So, let us start lecture 40. And we will continue our discussion on case studies on corrosion event and try to explain with the help of mixed potential theory. In fact, in the last two cases we have looked at two instances. One is when we have galvanic coupling of an active metal with a noble metal, where the areas of both the components were same. And the second case we looked at the effect of an oxidant or oxidizer on the corrosion rate of a metal, active metal. So, in both the cases we could see that the concept of mixed potential theories are met, that means it achieves a mixed potential, and then at that potential the net corrosion current densities is equal to the net cathodic current density. So, we could see that first instance mixed potential is achieved, and second part I c equal to I a, and here I a, since there were in both the cases we considered only one corrosion event, which is I a. So, is equal to I core, and we could see in that case the total reactions are broken into, in first case, first example, it is broken into hydrogen evolution, and second case metal dissolution, case 1, and in case 2 hydrogen evolution to ferric ion reduction, and third metal dissolution. Case 2. In case 1 we had only one cathodic reactions, but this cathodic reaction was taking place on two surfaces. One was on zinc surface, another one was platinum surface. And in the case of second case we had two cathodic reactions, one is hydrogen evolution, one is ferric ion reduction, and one oxidation reaction in both the cases, metal dissolution, which is the main oxidation reaction or corrosion reaction happening in both the cases. Now, if I try to look at case 1 carefully, we had the situation with the area of cathode equal to area of anode. Now, we had already explained the situation when we have a situation like let us say copper, and in between you have a iron rivet, this is copper, and if this particular component with the iron rivet joint is placed in an electrolyte, we did see that the rate of iron rivet corrosion has gone up enormously, because there the cathodic component has got a higher area as compared to the anodic component area, and that increase in area ratio, which is nothing but area of cathode divided by area of anode. So, this area if it goes up, I could see the rate of corrosion of active component goes up enormously. And there we could see that of course, the current density, the effective current density on active component has gone up because of larger number of cathodic reactions on the larger area of cathode. So, this particular situation, the effect of area ratio, this is our case 3, the case study is 3. So, let us explain this particular situation. In order to do that, we have to first look at the peculiarity in this particular situation. As we have seen that the Evans diagrams in first two cases, we explained on the basis of E versus log I. This I is the current density, and we saw that this is by mixed potential, this is E0 of metal dissolution, this is I0 metal dissolution on metal surface, and this was my hydrogen evolution of I0 on metal surface, and this is E0 of hydrogen. So, that was the pattern. This particular potential was E core and this particular current density was I core, and here I could see IC equal to IA. This is no problem, but interestingly that time this was on 1 centimeter square area, this was on 1 centimeter square area. For the time being we consider 1 centimeter square, it can also consider 1 meter square, does not matter. So, that means they have the same area. But when we have, let us say this hydrogen evolution reaction is taking place on 1 centimeter square area and it is taking on, let us say 110 centimeter square area. Since it is I0 and of hydrogen evolution and it is on the same metal surface, and if temperature, pressure, the surface condition of that metal, if these are not changing, the only thing that is changing is the area, then these two would have same values, because they cannot change. This is exchange current density, which is basically the number of reaction, cathodic or anodic reaction per unit area when the system is in equilibrium and reversible condition, and that to non-corroding situation. So, if I consider in this particular diagram, if I need to consider this area effect, we will not be able to do it, because if it is 1 centimeter square or 10 centimeter square, it will lie on the same point, and if it is the same metal, it is not an issue, because both the cases it will lie on the same point. But if let us say the situation arises when 1 centimeter square metal is connected to 10 centimeter square platinum or noble component, so then I0 hydrogen on metal and I0 hydrogen on platinum surface, they would be different. If it is so, this value would be greater than this. Now, whether it is on 1 centimeter square platinum surface or 10 centimeter square platinum surface, both the cases this value would remain same. So, then if I have this point to be my I0 of hydrogen evolution on platinum surface, so then whether it is 1 centimeter square or 10 centimeter square, it will lie on the same point, and accordingly I have the new mixed potential and accordingly new corrosion current density. So, actually it should be here, this point. But as we have understood from this example that if we have a higher area of that noble component, then the corrosion rate of the active component increases enormously. But on this Evans diagram, if we consider current density, I could see that whether it is 1 centimeter square or 10 centimeter square, it does not matter, the corrosion rate remains same. So, that means it is missing something, this events diagram is missing something. Now, in order to tackle this, if we consider current instead of current density, we would see that this can be explained in the same by the same events diagram. Only change would be, instead of current density, we will shift to current. Now, current density is I by A and current is I. Now, if it is 1 centimeter square, 1 centimeter square, so the I would be same as I by I magnitude wise, but once it goes to 10 centimeter square, then I will not be equal to I magnitude wise, because I would be always I by A, but the small I would be I by A, capital I by A, which is current by area, but when we have 10 centimeter, then I would be equal to, capital I would be equal to I into 10. So, then I could see that current value is changing. Now, if I look at the Tafel equation, this is beta, general Tafel equation, log I by I0. Now, this I could be IA or IC, this is IA, IC, I0 would remain like this, and that time this would be A or C, anodic or cathodic polarization. Now, this I can write it as beta log I by A, I by I0 by A. I can write this. So, this can be converted to log I by I0, capital I by I0, which is current. Now, if I try to plot the current instead of current density in that events diagram, we could see a difference. Now, let us say this is log I, which is ampere, or this is ampere instead of ampere per centimeter square, this is E in volt. This point, let us say E0 M2 plus, let us say 2 plus M is this value, this is I0 M on metal surface. It would have its own cathodic and anodic polarization plot, and let us say this is my E0 hydrogen evolution, let us say this is 0 volt, and now this point is I0 hydrogen on metal surface, and here I am writing area as centimeter square or 1 centimeter square area, and this is also 1 centimeter square area. Now, instead of I0, I write now capital I0. Here also it should be capital I0. Now, accordingly, because the equation for the cathodic as well as anodic polarization would be same as before, only thing is I am converting small I with capital I. So, this will also follow the same track. This. So, this is my I core, this is my E core. Now, if we have platinum of 1 centimeter square area, this will be I0 H2 on platinum surface, and then accordingly I have so now this is my new E core. Let us say 2, this is 1, this is 1, and accordingly we have I core 1, sorry 2. Now, interestingly, if I try to see the relation between these two, since I am not changing the area of the metal, it would be magnitude wise, it would be equal to I core 1 equal to, this is I core 1 magnitude wise, this should be equal to I core 2, since I am not changing the magnitude. But now, if I change the area of the platinum, this is let us say platinum of 10 centimeter square area. Now, I 0 equal to capital I 1 centimeter square 0 by A, or I would say I 0 by A 0. Now, if A 0 equal to 1 centimeter square, then I 0 equal to capital I 0 equal to 1 centimeter square. So, this is equal to I 0, but A 0 equal to 10 centimeter square, then I 0 10 centimeter square on 10 centimeter square would be I 0 into 10 centimeter square, and this I 0 is on 1 centimeter square area. So, now I could see that the I 0 of hydrogen evolution on 10 centimeter square is increasing. That means, the exchange current on 10 centimeter square area on platinum is increasing. So, now this point would be I 0 hydrogen on platinum of 10 centimeter square. So, it would have its own polarization, and then you have to add this current density, because this particular part is for 1 centimeter square. Now, I have replaced this 1 centimeter square platinum area with the 10 centimeter square platinum area. So, the hydrogen evolution is taking place on 1 centimeter square area of metal and 10 centimeter square area of platinum. So, this current density and this current densities are to be added for getting the total cathodic current densities. So, I just add them. So, only thing is it will be little bit closer than what we had here, because it is in the log scale. So, this is the part. So, now if I extend it, this is the new E core case 3, and this current density is the I core or capital I core case 3, and since the area of metal is not changing, which is still remaining same 1 centimeter square, is equal to I core, since equal to current density magnitude wise. Remember, this is magnitude wise. When I am writing this, this is magnitude. Their units are different. In this case, it is ampere, and in this case, it is ampere per centimeter square. Since its area is not changing for metal, so that is what this value would be equal to this. Now, you see that what is the change in the current density for anodic reaction. Now, in the beginning, when there was no connection between active and noble metal, my IA was at this point, and at this point I have IC equal to IA case 1. This particular region, this particular part, here again IC equal to IA situation 2, and here also I could see IC equal to IA equal to I core, and in this case IC is basically this current and this current densities, rather current. Now, here we have to add current, because now we are changing the area. Now, once we could see this IA has gone up enormously if I see the log scale value. So, the corrosion rate, why the corrosion rate of the active component increases? If we increase the area of the noble component, that can be explained with the help of Evans diagram. Rather, it is modified Evans diagram, modified because Evans diagram is basically E versus log I, but here it is E versus log capital I. Now, we could understand why the corrosion rate of that active component increases when it is joined to a metal which is noble and of larger area, and that explains the effect of iron rivet dissolution when the copper area is very large and the rivet area is very small, and this particular situation is explained better by this Evans modified Evans diagram. So, this is about case 3. Let us consider another case, which is case 4. The case 4 is about effect of presence of oxygen. Let us say in acid medium, let us say HCl, we have zinc piece, and if it is aerated, so that means we have oxygen, that case we see that the corrosion rate of zinc increases to a large extent as per our previous understanding. It can be also explained with the help of Evans diagram. This is log I ampere per centimeter square. I just missed one point here. The unit is ampere, but if we see here, the unit is ampere per centimeter square. Now, coming to this is E. Let us say this is zinc plus zinc E0 equal to 0.76, of course minus sign, and this is H. Let us say this point is E0, H plus H2 equal to 0 volt, is in volt, and oxygen in case of acid medium, oxygen evolution reaction, oxygen reduction is like this. This is oxygen reduction, and the potential E0 equal to 1.227 volt. So, I put it as 1.227 volt equal to E0 oxygen. So, this is the E core and this is the I core when there is no dissolved oxygen. Now, once we have dissolved oxygen, so this is I0 of dissolved oxygen on zinc, and this is I0 hydrogen evolution on zinc, and this particular one is I0 zinc on zinc surface. So, it would also have its own polarization. So, this is my own polarization, its cathodic polarization, and it has to move downwards and this has to move upwards because the mixed potential should lie between these two extreme potentials. So, now once it reaches to this potential, it is coming across another cathodic reactions. So, the total cathodic reaction should be added up. So, we add up and then we extend this. This is my new corrosion rate. So, this is I core case 2 when we have oxygen presence, and this particular potential is E core 2 case 2 when we have oxygen. And remember, when we have this, the hydrogen evolution reaction on zinc surface is decreasing to a great extent because of depolarization effect. So, this is the similar situation when what we had in case of presence of Fe+3 in the acid medium. So, let us stop here. We will continue our discussion. There will be one more lecture which will be concluding lecture, and there we will consider one more major 2 case studies, and then we will conclude for the corrosion 1, and then we will see what the more understanding on corrosion in the phase 2, which is the corrosion 2. Let us stop here. We will continue our discussion in the next lecture. Thank you.